Welcome friends to this new lecture of soil science and technology, and this will be our lecture 4 for week 5, and we'll cover in the next two lectures we'll cover two important topics, that is catenation capacity, and then we'll be covering the adsorption of different pesticides. The last three lectures we have covered important aspects of soil chemistry. We have covered details about the silicate clays, and we have also covered the sources of charge on clay colloids, especially the inorganic clay colloids. And today we will be starting a new topic, that is catenation capacity, and also we will be talking about annihilation capacity simultaneously. So, what is catenation capacity? The first question comes to our mind, what is catenation capacity? So, this is the first concept which we will cover today, and then the rest of the topics are methods for determining the catenation capacity. Then catenation capacity of different soils. We will discuss what is the relationship between the pH and catenation capacity, and then we will discuss about the CEC in field soils, and also we will try to see what is the relationship between different weathering intensity and catenation capacity as well as annihilation capacity. So, let us start our discussion. So, basically you know that in clay as well as in organic matter which is present in the soil, they are highly reactive because of their charge charge distribution. And as I have told you that these clay minerals or silicate clays or crystalline silicate clays create a huge amount of both positive and negative charges, especially the negative charges due to isomorphic or isomorphous substitution, and these negative charges are responsible for attracting different positive cations. So, basically the catenation capacity is the ability of the soil to exchange the cations from its surrounding medium and attach and absorbing and helping absorbing those cations over the soil surface or clay surface. So, catenation capacity basically also indicates the it also sometimes indicate the fertility status or nutrient enrichment status of the soil. So, the catenation capacity basically is expressed as the number of moles of positive charge adsorbed per unit mass of soil. So, unit of CEC or catenation, obviously the short form of catenation capacity will be CEC, and units of CEC earlier we use a unit called milliequivalents per 100 grams of soil for estimating the catenation capacity. However, the recent unit for catenation capacity is centimoles of charge per kilogram or C mole C per kg of soil. So, basically these two units are same. So, 1 milliequivalent per 100 gram is equal to 1 centimole of charge per kg of soil. So, in other words, soil with a CEC of 15 centimole per kg means 1 kg soil can hold 15 centimole of positive ions. So, let us go ahead and see what are the different methods of determining the catenation capacity. Now, one of the method is called the buffer CEC method. Now, what is buffer? Buffer is any chemical that resists the change. So, sometime you will see that we use pH buffer for measuring pH. So, basically it is some standardized chemicals which generally resist the change of chemical status. So, here in the buffer CEC method, basically we apply the buffer solution to the soil, and if the pH of the buffer is more than the pH of the native soil, then these methods measure not only the catenation sites active at the pH of the particular soil, but also any pH dependent exchange site that would become negatively charged if the soil pH were raised to pH 7 or 8.2. So, in summary, these methods exaggregate the true CEC of acid soils. And the buffer method, that is ammonium ions at pH 7 or barium ions at pH 8.2, measure the potential or maximum cationation capacity of soil. So, another term is called the effective CEC or ECEC. This is basically unbuffered. So, the unbuffered method can measure only the effective CEC or ECEC of the soil, and this method gives results when the pH of the native soil is lower than that of buffer pH. So, these are two general methods, and what are the different steps for determining the soil CEC? Now, you can see we are showing here 4 different beakers. Now, these 4 different beakers, and we are describing the process of measuring the CEC in some sequential steps. So, in the first step, if you can see, we are basically pouring the soil in some funnels, and we are leaching the soils with ammonium salt solution. Okay, sometime ammonium acetate. Now, these ammonium ions of this ammonium salt solution replaces the other cations. So, you know that the cations are calcium, magnesium, potassium, and then other H plus, aluminium. So, these cations are getting replaced by ammonium cation, and as a result of that, in the second step, you see in B means the second step, all the cations are coming into this leach solution, and ultimately all the exchange sites of the soil will be occupied by this ammonium cation. Now, so after removing, now in the second step, you can see all the soil has been saturated with ammonium. Now, our duty is to remove this excess of ammonium salt solution, then soil is again leached with K plus soil solution. So, to remove these ammonium attached or adsorbed ammonium cations, we further leach the soil with potassium salt solution. So, what happens? This potassium basically replaces these ammonium ions, and thus all the exchange site is further occupied by this potassium. So, ammonium washed into the lower container, and the concentration of the ammonium will be determined which the CEC of the soil. So, that will basically gives you the CEC of the soil. So, again at the first step, we will take the soil into a funnel, and then we will leach the soil with some ammonium salt solution, basically some ammonium acetate, and as a result of that, you will see that all the ammoniums will replace all the cations in the leach solution, and ultimately the ammonium ions will occupy all the exchange sites. In the third step, we will remove all the ammonium with the help of potassium salt solution by leaching with the potassium salt solution, and finally we will measure the ammonium in the container, and that will give you the idea of the total CEC. So, basically it is acting as a proxy for measuring the cationation capacity, because these ammonium will replace all these cations, calcium, magnesium, potassium, and ultimately it will show the total cationation capacity. So, let us go ahead and see how we can calculate the soil CEC from lab data. So, after leaching the soil with 0.4, let us assume that after leaching the soil with 0.4 liter of ammonium solution, all the exchangeable cations shown in the soil samples were displaced off the colloids and washed into the beaker along with the excess ammonium ions. So, the solution in this beaker B, that is in the second step, was analyzed for calcium, magnesium, potassium, aluminum, and hydrogen, or H plus ion, with the following results, and we are getting the following results, that is 200 milligram per liter of calcium ions, 60 milligrams per liter of magnesium, then 97.4 5 milligram per liter of potassium, and then 5 milligram per liter of H plus, and 67.5 milligram per liter of Al3 plus. So, because only 0.4 liter of the solution was collected from the soil samples and the soil sample weighted only 0.1 kilo. So, we can convert this result to by multiplying with 0.4 and 10 to give the amount of each ion collected in milligram per kg of the soil. So, as an example we can see the example for calcium. We are getting 200 milligram of calcium per liter, and then we are multiplying it with these two multiplication factor to convert it to milligram per kg of soil. So, basically we are getting 800 milligram of calcium ion per kg of soil. So, this is simple. So, let us see what is the next step. So, in the next step for calcium, the atomic weight is approximately 40 gram per mole. So, we can calculate the centimole of exchangeable calcium in 1 kg of soil. So, basically we have to convert this 800 milligram of calcium into a centimole of calcium. So, basically that 40 grams mean 1 mole. So, from there we can we can calculate millimole and centimole. So, basically when we convert this 800 milligram of calcium, we will get ultimately 2 centimole of calcium ions per kg of soil. So, our next step for this calculation, so once we calculate this centimole, now next step is to repeating this calculation for each elements and ultimately providing the which will ultimately provide the following results. So, we are getting ultimately 2 centimole for calcium per kg, 1 centimole magnesium per kg, 1 centimole potassium per kg, 2 centimole H plus per kg and 1 centimole of L3 plus kg. So, we are getting the concentration of each of the cations which were absorbed previously and ultimately contributing to the CEC of the soil. So, we have measured individual concentration in centimole per kg of soil. We have covered up to this point. Now, we have to multiply the centimole per kg for each element by the valency of the respective ion to convert it to the centimole of charge. So, from centimole to centimole of charge, you have to multiply with the respective valency of the cation. So, you will get the C mole C per kg of soil. So, for example, if we use the calcium again as an example, you can see we are here using 2 centimole of calcium per kg of the soil, and then we are multiplying it with 2 because the calcium valency is plus 2. So, we are getting 4 centimole charge from calcium plus ion, calcium 2 plus ion per kg of soil. So, for individual element we have to calculate this centimole of charge. So, repeating, we have to repeat this calculation and we will provide the following results like 4 centimole of calcium per kg, then 2 centimole of centimole charge of magnesium per kg, then 1 centimole charge of potassium per kg of soil, then 2 centimole charge per H plus per kg of soil, and 3 centimole charge of L3 plus per kg of soil. Now, assuming the 5 elements measured all the 5 elements measured account for nearly all the exchangeable cations. If we assume that there are no other exchangeable cation, then the sum of their charges, that is 4 plus 2 plus 1 plus 2 plus 3, that is 12, basically equals to the CEC of the soil. So, that is 12 centimole kg per centimole charge per kg. So, what are the steps? If you jot down, if you summarize, first of all we have to leach the soil with the ammonium salt, which will replace all the adsorbed cations into the soil into the leach solution. Ultimately, we will be leaching this ammonium with the help of potassium, and then these further leached down, all the ammonium can be calculated and it will basically, it will basically indicate the catenation capacity. Now, once we calculate the so for estimating the catenation capacity, we have to measure the concentration of individual individual cation which were replaced by ammonium. After after we calculate them, then we have to multiply some multiplication factor to convert it to milligram per kg. Now, after we convert it to milligram per kg of soil, then we have to convert it to centimole, because we know the amount or gram of individual element per mole, and from this centimole we have to convert it to centimole of charge per kg of soil. So, repeating all these things for all the elements, then we have to sum it to get the total catenation capacity. So, another method. So, if you remember, in the previous method, what we did, we basically measured the concentration of all the cations which were leached in the first beaker with the help of ammonium salt solution. However, if you remember the total process, at the end we are further leaching all the adsorbed ammonium with the help of potassium solution. So, by measuring the total ammonium concentration also, we can also measure the CEC. So, there are two methods. One method says that you measure all the cations which are previously replaced, or in the first stage the cations which were replaced in the first stage with the help of ammonium. So, you measure them individual, their concentration, convert them into their centimole and further centimole of charge, and then add them. It will finally give you the total centimole total CEC. Another method, the second method, says that you measure all the ammonium which were leached by the potassium in the last stage. So, you assume that ammonium concentration in beaker D, that means the last stage, to be 540 milligram per liter. So, as in the method 1, because of 0.4 liter solution was collected from the soil sample and the soil sample weighted only 0.1 kilo, these results can be further, just like the previous, these results can be calculated as follows to give the amount of ammonium ions collected for mg per kg of soil. You can see we are multiplying with the same multiplication factor, that is 0.4 and 10, to get a milligram of ammonium ions per kg of soil, and ultimately we are getting, and now in the second step we are converting it to centimole. We are ultimately getting 12 centimole of ammonium ions per kg of soil, and then these centimole will be, since ammonium has a single valency, so further we will be getting that answer is 12 centimole per kg. So, final our result CEC is 12 centimole C or 12 centimole 12 centimole charge per kg of soil. Now, what are the CEC of different soils? Now, the CEC of the different soils also varies widely from one soil to another soil depending on their chemical composition. So, sandy soils are low in CEC, but clay soils having high catenation capacity values. Why? Because the sandy soil are basically composed of sands, and sands are chemically inert, whereas the clay soils are made of these crystalline clay minerals which are chemically reactive because of their negative charge development. So, obviously, a clay soil will have higher CEC than that of a sandy soil. Now, iron and aluminum oxides, kaolinite, are having low CEC, that is less than 10 centimole per kg, and whereas mica and chlorite has 10 to 40 centimole per kg, and smectite and vermiculite ranges from 80 to 180 centimole per kg. And the humus, remember that humus is having the highest CEC, that is more than 250. Most of the time it is more than 250 centimole per kg. So, remember that among the clay minerals, if you compare clay minerals as well as the humus is showing more catenation capacity than rest of all the clay minerals. So, humus is much more reactive than the clay. So you can see based on the clay mineral nature or clay mineral type, the catenation capacity is varying, and you know the reasons behind this, because you know that in case of kaolinite there is no isomorphic substitution. So as a result of that, there is very less amount of negative charge development. When there is a very less amount of negative charge development, obviously their catenation capacity will be low. Similarly, so in case of smectite and vermiculite, obviously you will be having high amount of isomorphous substitution, in that octahedral layer. If you remember from our last lecture, then obviously there will be high amount of negative charge, and these high amount of negative charge will ultimately contribute to the high catenation capacity. Mica, you remember that both the layers, the interlayer space are collapsed by the small potassium cations, so there is no space for adsorption of the potassium ions. So as a result, it's also have intermediate ranges of catenation capacity. So we have a basic idea about the catenation capacity of different soils. So remember that at higher pH, soil humus contributes more catenation capacity to the soil with a constant amount of clay. So if you see, this is the relationship between organic carbon in gram per kg and catenation capacity, which has been expressed in terms of centimole of charge per kg. So if you go back to the previous, previous couple of slides, you will see that here you should replace the C mole at C mole C. Obviously, it should be centimole of charge. So please, replace this centimole with C mole C. I will try to change this while I will be distributing the PPT with you. Okay, so it will be centimole of charge per kg of soil. So let us move ahead and see. So what I was talking about, the relationship between organic carbon and catenation capacity in centimole of charge per kg of soil. So you can see that at pH 4 to 4.5 in this line, obviously at pH 4 to 4.5, 1 gram of soil humus increases the CEC of 0.13 mole per kg. So if you increase 1 gram of soil humus, because we are getting a slope of 0.13, so that means, so in this case, for this line, we are getting a slope of 0.13. That means if you change the the organic carbon by 1 unit, that is 1 gram per kg, you will get an increased CEC of increased CEC by 0.13 centimole charge. However, at pH 5 to 5.5, we are getting a slope of 0.26. So slope is higher. So once the slope is higher, obviously that interpretation will also change. So we are getting at pH 5.5, when you are increasing the organic carbon concentration with by 1 gram per kg, the pH will increase 0.26 centimole charge per kg. So you can see at higher pH, soil humus contributes more CEC. So higher pH we are getting here 5 to 5.5 and here 4 to 4.5. We are getting a CEC increase of 0.13 centimole C per kg here for 4 to 4.5. However, in case of 5 to 5.5, we are getting an increase of 0.26 centimole charge per kg, which is double than the earlier. So that means again it is re-establishing the fact that at higher pH, soil humus contributes more CEC in the soil with a constant amount of clay. That is a prerequisite that your clay has to be constant in both the condition. So let us see some common ranges of potential catenation capacity. I'm trying to show you the important soil orders and their corresponding CEC. So if you consider histosols, obviously we are getting the higher CEC because it is dominated by organic matter. So we are getting C-mole 110 to 170 C-mole C per kg of soil, and in case of vertisoil we are getting 33 to 67, and obviously in case of aridisoil, which is dominated by sand, we are getting lower, somewhat lower. Spodosol we are getting lower. So in case of oxisol, which is basically dominated by iron and aluminum oxides, we are getting very low, which is 2 to 13. So you know that in case of iron, aluminum oxides and kaolinite, there is low amount of CEC. So that is the reason that we are getting low amount of catenation capacity in case of these oxisols. However, in case of histosols, we are getting high amount of catenation capacity. So let us do some let us solve some problems. So we want to estimate the catenation capacity and clay mineralogy. So we want to estimate, in the first step we want to estimate the catenation capacity from soil mineralogy or clay mineralogy. So the dominant clays in mollysols are likely 2:1 type, such as vermiculite and smectite. Thus the average CEC of the clays of these types to be about 100 centimole per kg of clay, 100 centimole charge per kg of clay. So at pH 7, the CEC of organic matter is about 200. You know that I showed you in the last couple of slides the ranges of CEC for organic matter. So it will be, we can assume it by we can assume it as 200 centimole per kg. Since 1 kg of this soil has 0.20 kg, that is 20% of clay, and 0.04, that is 4% of organic matter, we can calculate the CEC associated with each of these sources. So let us see what are the CEC from each of these sources. So from the clays in the mollisol, we are getting 0.2 multiplied by 100 centimole charge per kg. So that is 20 centimole charge per kg. So basically we have to multiply the respective catenation capacity with the fraction of that mineral which is present in the soil. So we are having, we know that here it is 0.2 kg clay mineral we are getting in 1 kg of soil. So from organic matter of the mollisol we are getting 200 multiplied by 0.04, which is 4%. So we are getting 8 centimole charge. So ultimately the total CEC from the mollisol will be 20 plus 8, that is 28 centimole charge per kg of soil. So it is a one type of solution, and if we try to estimate the clay mineralogy from CEC, we assume that a soil contains 60% of the clay and 4% of organic matter, and at the pH 4.2. So you also know the CEC is 5.8 centimole charge per kg. So you want to estimate the types of clays present. So at pH 4.2, the CEC of organic matter would be comparatively low, around 100 centimole charge per kg. So therefore let us estimate. So we estimate that is CEC from organic matter in 1 kg of soil. Obviously it will be 0.04 kg organic matter, that is 4%, multiplied by 100 centimole. We have assumed that 100 centimole charge. So it will be 4 centimole charge. The remaining portion of the CEC contributed by the clay can be estimated at. So the total CEC is basically contributed by both clay mineral as well as organic matter. However, we have already calculated the CEC which has been contributed by the organic matter. So the rest of the CEC will be automatically contributed by clay in 1 kg of soil. So the rest of the CEC will be 5.8. We know the total CEC, and we are subtracting the the centimole charge which is coming from organic matter. So 1.8 centimole charge. So this 1.8 centimole charge has to be contributed by the clay. So since 1.8 8 centimole per charge per kg of soil is provided by 0.60 kg of clay, that is 60% of 1 kg of soil, we can estimate CEC of the pure clay is basically 3 centimole per kg of clay. Now, from the previous table which I showed you, different order, if you can, if you can compare that previous table, we can identify the soil and the soil order by their respective CEC. Now, we are getting 3 centimole charge per kg of clay. So, if we go back to the previous table, so basically we will be ultimately getting a CEC which can be contributed by either oxysols, either ultisols or spodosols, because they have the range which covers that 3 centimole charge per kg of soil. So, from that you can calculate, you can identify the soil order, not only the soil order, but also you can get a hint about the clay mineralogy. So, guys, I hope that you have got some basic ideas about the catenation capacity and how we calculate, how we estimate the catenation capacity in this lecture. And we'll try to finish this lecture, we'll try to finish this topic rather in this coming lecture, and then we'll be covering also the annihilation capacity, and then we'll go to our next topic. So, since then, thank you very much.